Imagine this. Havana, 1995. The Caribbean sun beats down on streets lined with chrome and steel from another era. Tail fins shimmer in the heat. Candy-colored Chevrolets, Fords, Buicks, and Cadillacs from the 1950s rumble past crumbling colonial buildings, still alive decades after Detroit forgot them. These cars were never supposed to survive this long. Yet here they are, patched together with ingenuity, stubbornness, and whatever parts could be found. But beneath the beauty, there's a crisis. For nearly 40 years, Cuba has been cut off from American spare parts. The U.S. embargo has squeezed the island's supply lines tight. Then the Soviet Union collapses, and with it goes Cuba's discounted oil lifeline. Fuel imports plunge by more than 80%. Gasoline becomes rarer than gold. When you can find it, a single tank costs more than many Cubans earn in an entire month. And in a modest garage on Cal 23, a mechanic named Julio Alvarez stares at a wounded 1956 Chevrolet Bel Air. The car has a blown head gasket. Its owner can barely afford repairs, let alone the $20 it would take to fill the tank if gasoline were even available. The numbers don't make sense anymore. A car that gets 12 miles per gallon in a country where the average salary is about $20 a month is not transportation. It's a burden. But Julio isn't thinking about gasoline. He's thinking about what restaurants throw away every night. Behind Havana's cafes and roadside food stalls, metal drums overflow with used cooking oil, dark, thick, and unwanted. Oil that costs nothing. Oil that nobody values. Oil that, in theory, contains energy. And that's when the question forms. What if this 265 cubic inch small block V8 could run on French fry grease? To understand how radical that thought was, you have to rewind to 1955, when Chevrolet introduced the small block V8 that would become one of the most legendary engines in history. GM engineers designed that 265 to run on high-octane gasoline. Every dimension, every ratio, every curve in the combustion chamber was calculated for one specific fuel. The compression ratio sat at 8:1, tuned for leaded gasoline. The Rochester 2-barrel carburetor mixed fuel and air at the precise 14, 7:1 ratio for clean combustion. The fuel pump delivered just the right pressure for gasoline's thin, watery consistency. Gasoline vaporizes easily. It ignites quickly. Its flame front moves at roughly 30 feet per second. The engine was built around those properties. Millions of dollars and thousands of engineering hours went into perfecting that chemistry. Vegetable oil, on the other hand, behaves like a completely different substance. It's thick, especially when cold. It doesn't evaporate easily. Its flash point is dramatically higher than gasoline's. And it burns slower. Diesel engines can handle oils like that because they rely on compression ignition, squeezing air so tightly that fuel ignites without a spark. But gasoline engines depend on spark plugs and carefully atomized mist. They were never meant for cooking grease. So, what happens when someone tries? The oil refuses to flow through narrow fuel lines. Carburetors can't atomize it properly. Instead of a fine mist, the engine gets heavy droplets. Spark plugs foul. Carbon builds up. The engine keeps running after you shut it off because hot deposits ignite the fuel on their own. It's mechanical chaos. Detroit engineers would have dismissed the idea instantly. But in Cuba, impossible is just another obstacle. Julio understood something the original designers didn't have to consider. When you don't have fuel, you either innovate or you walk. His breakthrough began with simplicity. He installed a second fuel tank dedicated to vegetable oil while keeping the original tank intact. The car would start on conventional diesel fuel, easier to obtain in small quantities and more stable at lower temperatures. Once the engine warmed up, the system would switch to heated vegetable oil. Heat was everything. Julio wrapped copper tubing around the exhaust manifold, creating a homemade heat exchanger. As exhaust gases warmed the manifold, they transferred heat into the vegetable oil before it entered the engine. At around 180 degrees Fahrenheit, the oil thinned dramatically, flowing almost like diesel. That temperature wasn't a guess. It was tested. Too cool, and the oil stayed thick. Too hot, and it degraded. Then came the switching process. Start on diesel. Run for several minutes until the oil reached optimal temperature. Flip a manual valve and operate entirely on vegetable oil. Before shutting down, switch back to diesel briefly to flush the system clean so oil wouldn't solidify overnight. Simple, mechanical, reliable, but There was a larger problem: the carburetor. Even heated oil was too heavy for proper atomization. So Julio did something radical. He eliminated the carburetor entirely. Using salvaged parts from a Soviet tractor and a Mercedes diesel injection pump pulled from a wreck, he engineered a mechanical fuel injection system that could deliver thicker fuel directly and precisely. He even modified injector nozzles to change spray patterns, compensating for vegetable oil's slower burn rate. Injection timing was advanced to ensure peak pressure occurred at the correct moment in the power stroke. Then he tackled filtration. Restaurant oil is filthy. Food particles, water, burned residue. If that enters an engine, it's catastrophic. Julio built a three-stage filtration system. First, layered cloth filters removed large debris. Second, a repurposed truck oil filter caught smaller particles. Finally, a salvaged laboratory centrifuge spun the oil at high speed, separating microscopic contaminants and water. Water was especially dangerous. In an engine, it doesn't compress, leading to hydraulic lock and catastrophic failure. Julio's centrifuge reduced water content to negligible levels. When the system was complete, the results were astonishing. Fuel costs dropped roughly 90%. Performance barely suffered, horsepower dipped slightly, but torque actually improved, thanks to the oil's longer burn duration. The engine ran smoother and quieter. And emissions? Dramatically cleaner. Vegetable oil combustion produced far less particulate pollution, almost no sulfur dioxide, and significantly lower carbon monoxide. The exhaust smelled faintly like a kitchen instead of raw fuel. After hundreds of thousands of miles, the engine showed surprisingly low wear. Vegetable oil's natural lubricity protected cylinder walls better than gasoline ever had. Word spread quickly. Mechanics across Havana came to learn the method. Within 2 years, thousands of classic American cars were running on cooking oil. Restaurants began selling their waste oil instead of paying to dispose of it. An underground economy formed around collection, filtration, and conversion. Each engine required adjustments. Ford flatheads, Chrysler Hemis, Buick nailheads, all slightly different. Compression ratios were modified where necessary. Injection timing refined. Glow plugs were added for cold starts. Julio documented everything in handwritten manuals that circulated among mechanics. By the late 1990s, an estimated 3,000 vehicles had been converted. By 2010, that number had grown to roughly 15,000, including buses and farm equipment. The environmental impact was enormous. Millions of gallons of gasoline displaced. Hundreds of thousands of tons of CO2 avoided. And all of it accomplished without billion-dollar research labs, without government subsidies, without chemical biodiesel processing plants. Modern biodiesel requires methanol and caustic chemicals to convert oil into esters. Julio bypassed the chemistry entirely. Heat it, filter it, inject it. When European researchers eventually discovered what was happening in Havana, they were stunned. Solutions they had spent years trying to perfect electronically were being handled by a $5 manual valve and mechanical timing adjustments. The 1,956 Bel Air that started it all kept running. 200,000 miles, 300,000 miles, 400,000 miles. The engine rebuild at 300,000 wasn't due to vegetable oil failure, just normal wear. By the time it crossed 500,000 miles, the car had become legendary. Tourists rode in it without realizing they were sitting inside one of the most practical demonstrations of grassroots engineering in modern history. Julio never patented his system. Under embargo, patents meant nothing anyway. He never grew wealthy. He simply kept working, converting cars, teaching others, refining the system until his death in 2018. His funeral procession was led by vehicles running on cooking oil, a moving tribute powered by the very idea he proved possible. What makes this story powerful isn't just the engineering, it's what it represents. For decades, the world has been told that solving energy and environmental problems requires massive funding, cutting-edge technology, and corporate innovation. Yet a mechanic in Havana showed that 1950s engines could run carbon neutral using restaurant waste and mechanical ingenuity. He demonstrated that adaptation can rival invention, that simplicity can outperform complexity, that necessity can out-engineer billion-dollar budgets. Somewhere in Havana today, an American V8 built before most of us were born is still running on used cooking oil, smoother, cleaner, and cheaper than anyone in Detroit would have believed. All because one mechanic refused to accept that something couldn't be done. It makes you wonder, what other impossibilities are simply waiting for someone desperate and determined enough to challenge them?